I'm sorry, we can hear any sound. Sorry.
Do you hear now?
Yes, now I can hear you, even if it's a little bit noisy.
Well, sorry for this. Now you see the presentation.
Yes, but in the presenter mode.
Okay. Okay. So I continue to speak uh, um, about my paper. The main objective of research is we start with a description of concepts and the need of sustainable urban mobility plan. Uh, how can we use this smart equipment, which name Smart Hub, to collect the data um, traffic, from road network, and how we can use this data to develop a transport model, to calibrate and validate the results. If, as you know, our society in last period have some goals for sustainable development, and one of these goals, number 11, is addressed to sustainable city. So in last period, a series of cities start to develop and implement a sustainable urban mobility plan, which is a strategic document with action and measure to reduce the pollution, to reduce the congestion, and to and try to have a sustainable mobility. How is develop this kind of strategic documents? Is are four steps. First step is to preparing, to identify action and goals for sustainable urban mobility plans, to elaborating the plans, which include normally transport model, because if you want to test some action, some measure, the simulation model is a good tool, because it's better to know if what happens if I will build a new trip in simulation like in reality, and to implementing the plan. But to develop this transport model, I need to use our mathematical knowledge to write the relation, to put, to collaborate data and to obtain the results. But the most important is to have some input data, because if you have good input data, also results are good. But if you have a bad data, the results are certainly bad. So, which kind of data I need normally? I put here, I split in two components. Static data, and we can obtain information from national, regional, and local authorities. I need information about public transport, uh, and of course, I can use the previous studies to collect this kind of information. Dynamic data are survey, are mostly obtained through survey, traffic survey, and household survey. And of course, I need traffic count, the travel time measure. But the main problem is this last two type of data are very expensive to obtain. I write here approximately more than half of budget go to people who collect this kind of data, staying in taxation and count how many vehicles, how many buses, how many bicycles go. So, a solution to reduce this price is to use smart equipment. Are a set of advantages. Data are collected in real time. I can extend the time period as as much I consider. Uh, Classification level can be dynamic adjusted because every city is special. In some city, I don't know. For example, in Italy, maybe people use scooter, but in Belgium they use bicycle. In Romania we use only cars. It's something special for us. Um, of course, are some limits. These limits are technological, uh, cost, and the hazard. Because if I don't know all situation, the apparition of hazard can give me some errors. And taking in consideration all of advantages and limits, uh, our teams from university will develop this kind of equipment. We say his name is Smart Hub. This equipment have a lot of components, the best components in the market. It's not was not cheap to develop. We have a project, and this equipment have a series of sensors, external sensors like camera, uh, um, LoRa, no, not LoRa, sensor to detect car in parking area. We have software to identify car, pedestrian, bicyclist, and also we have a very powerful server who can process image and video flow. How is developed? This equipment is developed to work like a single equipment, but also can communicate with other equipment to build a network. And it's developed to respond to the most important service of smart city, and these services are smart mobility, smart people, smart governance, smart economy, smart living, and smart environment. Here I have how it's looking. I have hardware architecture and some features from reality. Is a box mostly, where put uh, the component for the process, and in the left picture we have um, camera, variable message sign, to give information to people, and the metro station. And in the right we have a parking space with some sensor to detect if it's parking place is used or not. Which data we collect? We collect data about private transport. This is the counting: how many cars, how many bicycles, how many private vehicles. Data about public transport, because I want to know when the bus arrives, if it's in time or have a delay, or is um, the opposite delay before time. Um, we collect data about the license plate number of private vehicles, because sometimes it have some restriction. So I want to know if this private vehicle respects this restriction. And also the equipment can pair license plate number to obtain matrix origin destination, to calculate travel time, to see we have some congestion, we have some delay in traffic. And of course, we have a statistics, a sustainable urban mobility plan for medium cities located near Bucharest, where our project was implemented. Um, we build the transport model, we develop a network model, demand model, and impact model. We classify the vehicle in private transport, car, private vehicle, taxi, motor, electric scooter, and pedestrian, and public transport. The demand model was a typical demand model in 4 steps: trip generation, trip distribution, modal choice, share assignment. And from one step to another step, we use data collected with smart equipment to make calibration of and to see if our parameters are well calculated. And this is the result, the flow inside the city. And here I have the data collected. We have the value for recorded value, and the model, what we obtain from a model. How you see the difference was small, not in first step, but after calibration, the difference was from 1 to 3% per 100. Okay, and some conclusion. The innovation appear in our research because in last period, the apparition of artificial intelligence help us to develop new technology. The most important is the research results. We obtain something physical, this equipment, and we can use it. And of course, we have some limitations because we observe it's very important how you put camera in traffic, because camera, if it's not well oriented, you can have some errors. Also, weather condition can affect your recording. And what's special, I don't know in another country, but in Romania, if you want to collect data about plate number, it's not very easy, it's not legal. So you must obtain from authority a document. And when we put the results, we make an anonymous process to hide the number. And the future research will be focused on develop of dynamic model for traffic monitoring and control. We want to export the results to a system who can control the light intersection, so we can optimize the traffic flow. Okay, thank you. I hope If you have any questions. If there are not questions, we can go to next presentation.
Sorry.
Okay. Okay. We remain alone. So the next, we can go to next presentation.
Yes, please. But they can. I think they can speak because they were the speaker. Yes, Professor Francesco, could you open your microphone?
Professor Russo, they
Yep.
ask you to. Okay, I think that you can intervene if you want.
Just a very small question. Do you speak about the calibration of the model? Do you hear me?
Yes.
Yes, it's a little loud, but I will try to.
Sorry. Do you speak about calibration of the model? I read in the slide, if I don't remember, but the number 20, you speak about calibration of the model, but the first part of your in the band was very difficult to hear. Can you repeat which model do you calibrate with your specific smart device? Which specific model do you speak about?
Um, in our transfer model, we use the demand model in four steps, and we use the data collected to calibrate the last step, the trip assignment, to see if the value from model are, are we meet the gap between the value from the model and the value from counted with our equipment. So we have a calibration process, and of course we have a validation process. The calibration in calibration process, with the value from we put our equipment in on 5 points from this city, and we collect data from this point, and we use data for calibration, and of course we use data from center of the city for validation to see if our calibration process was good. It's not one from first step. Okay, we repeat it as is normal, but finally we have some value who can who was good in our opinion.
Thanks.
Okay.
There is another question. No, okay. And next presenter is here.
Yeah.
I don't know which. Mario Pozzo.
I'm apologizing. I think that is scheduled Giuseppe Cappelli for the next presentation. I will present the next one, the next following the one presented by Giuseppe Cappelli.
Do you hear me?
I can hear you, Giuseppe.
Okay.
I don't know if organizer is hearing you. Sorry, can we start?
We can't hear the colleagues in Turkey, but we can hear Mr. Capelli.
Okay. So there is
Thank
a
you.
problem with the connection with the Turkey session. Okay.
Probably, or the microphone is muted, something like that.
Okay. Okay, yes.
Okay.
They
Thank you.
unmute, they mute the microphone in order to avoid noise. Giuseppe, you can start.
Okay. Let me share. Okay. I think that you can see my screen, hopefully.
Yes.
Okay, thank you. First of all, good morning to everyone. And before starting the presentation, let me introduce myself. My name is Giuseppe Cappelli, and currently I am a research fellow at the Department of Civil and Mechanical Engineering at the University of Cassino in Southern Lazio in Italy. I want to show you this preliminary result related to this work. That is work related to a project conducted in Italy and a project that in which I was involved in the last 6 months, more or less. The title of this presentation is Interaction between Drivers and Road Infrastructure Characteristics, combining OBD and geographic data to classify traffic behavior with feed-forward neural network. Before starting the presentation, I will follow this roadmap. So after a brief introduction, the focus will be on the methodology aspect, and so how data are collected and which model are used. Then the result, and as last section, we draw altogether the conclusion. The reason why to study driver behavior is that humans make mistakes, as is stated from the safe system approach that is the main the main plan that is behind all these safety plans among all over the world. If we want to define driver behavior is a set of action that road users undertake to make their driving task. So in a context, in urban context and in an ex-urban context. According to the literature, 90% of road crashes are due to driver behavior. So it is essential to study driver behavior not only to reduce the risk related to road crashes, but also to improve sustainability. According to the literature, if we undertake some safe behavior, this safe behavior are related also to reduce fuel consumption and improve sustainability aspects. In this presentation, I will show you how driver behavior have been studied. And in this paper, we used onboard diagnostic data, OBD, that are data retrieved from the CAN bus network that give information on internal information such as speeds, speed engines, and so on. And we combine this OBD data with geographic data. Then we trained and tested an artificial neural network to solve this classification problem. And we saw that this model give good prediction accuracy to predict driver behavior. The first step in this methodology was to select the best dataset to use. After studying and reviewing some of the most used dataset, we decided to choose the Davis Driving Dataset 2020 because this data contain almost 51 hours of driving recording over 4,000 kilometers of driving. And another advantage of this dataset was that all these data were georeferenced. So we have also GPS information on data that are collected during this experiment. As we can see in this slide, I show you which are the main variables that are retrieved from this OBD data in the Davis driving dataset. We can see engine speed, for instance, brake pedal status, accelerator pedal position, vehicle speed, and so on. This dataset, as I told you, was the largest dataset available, and also a dataset that contained georeferenced information that was used to combine this dataset with external information retrieved from OpenStreetMap, for instance. After that, there was the feature selection phase. With feature selection phase, we selected the most important feature according to what emerged from the literature. We extracted the features with reference with accelerator pedal position, engine speed, vehicle speed, and so on, as it's possible to see in the table on the right of the slide. After this feature selection phase, we applied an unsupervised labeling approach. And this labeling phase falls under the preprocessing phase. So we have this data, and then we use these key mean algorithms to cluster all this data. And we decide to cluster this data in three main clusters. The first cluster refers to safe driving, the second one to normal driving, and the third one to dangerous driving, so to risky behavior. In the table, we can see the description of the three clusters identified, and also the number of data that falls in within the cluster. One of the main steps, and also an important step of this methodology, was the geographical data enrichment. We try to merge data from the OPD, and we merge this OPD data with OpenStreetMap data, because the aim of this study, but also of this paper, was to understand to understand the role of the external environment on driving behavior. So it was an essential part of this research. After that, we trained and tested a multi-layer perceptor neural network that is an artificial neural network that works by emulating brain's neural process. With this model, we were able to classify driving behavior according to the three classes identified with the Kimian algorithm, and we saw that the performance of this model was very high. As it's possible to see in this results slide, we can see that if we focus on the first figure on the right, at the top of the slide, we see that after almost five epochs, the train loss go from 0.3 to 0.05, and that show the model's ability to fit the data. And then if we see the accuracy during the different epochs, we can see that the accuracy increase rapidly to a sort of threshold value that is about 0.98. So 0.98 for the accuracy metric is something that is very high. On the figure on the in this case on the left, the orange curve represents the performances of the model on the test set. So we see that the performances of on the test set are slightly below of the performances of the training set that usually are higher than the test sets. Lastly, in this slide, there is also a representation of the results by showing the confusion matrix. On the terms on the diagonal of this main diagonal of this matrix, we can see the number of observations that are correctly classified, And if we see the confusion matrix on the right, we have put in this matrix the percentage of correctly classified observation. So the correctly classified observation starts from 97% and reach value of 99%. That means that the model is able to correct classify observation in a robust way. Going to the conclusion, the takeaway message is that it is essential to study driver behavior because humans make mistakes, and humans' mistakes and errors are the leading cause of road crashes. As it possible to observe from the current literature, try to reduce aggressive and unsafe driving behavior is something related not only to safety aspect, but also to sustainability and so reducing fuel consumption and protect the environment. In this paper, we use this Davis training dataset and also geographical data to create this model that is a multi-layer perceptual neural network. And at the aim of this paper was to test a reliable model to predict driving behavior. This tool is a useful tool, for example, to make large-scale analysis, but there are also some limitations. The first one is that an American dataset, a USA dataset, was used to make this analysis, and not an Italian dataset, for instance. And the second one limitation is that there is no a variable importance analysis performed. So we are currently working on how to find a way to understand which are the most important variable related to safe, moderate, or unsafe driving behavior. Thank you for the attention, and thank you for hosting us in Turkey. Thank you. I don't know if there are any questions.
We can hear you. Sorry.
We can't hear you. It's not a problem of the. We can't hear anything from the Turkish colleagues. At least I can't.
We can hear each other in remote connection, but we cannot hear any Turkish colleague. Sorry.
Okay. Now?
Yes, yes.
Okay. I have a question about the neural network used. I want to know the software used for training and test of neural network and for defining the architecture of the neural network, and then how many data in percentage were used for the training of the neural network and for the test.
Yeah, thank
Because
you.
the test give information about the generalization process of the neural network.
Okay, so the software that was used to perform this analysis and also to create the model was Python. We wrote this code in a Python code, and but we tested and trained also some other different model. And the best model, according to the accuracy metric, was this artificial neural network. Regarding the training and the test phase, we don't use a normal splitting between 80 or 20% because we used to validate the model across validation approach. So we split, for instance, the data in 10 parts, and we we tested the model on the first 9 parts of this dataset, and then we validate the model on the 10th part of the dataset, and then we move these windows ahead in order to repeat this. Yeah, exactly.
Okay. Thank you very much.
Thank you for the question.
Another question? Here we don't have more questions. If there's any online participants that wants to ask. Okay, thank you so much.
Thank you.
Next, we have Dapuzzo.
Hi.
Okay.
I'm ready.
Yes, you can start sharing.
Okay, thank you very much. Can you hear me?
Yes.
Okay, thank you. Good morning to everyone. Let me thank my co-author of this paper, Sofia Nardoianni, Giuseppe Cappelli, and Vittorio Nicolosi. I'm presenting a paper entitled Statistical Analysis of Experimental Crossing Speed on Vertical Traffic Calming Device, Influence of Vehicle Category and Road Safety Implications. I'm Mauro Dapuzzo, and I'm full professor highway design and traffic engineering at the University of Cassino. Let's go straight on the problem. Obviously, we are talking about road safety. Here there are some very short figures relating to road safety in Europe, showing that obviously there is a declining more that serious injuries involving vulnerable user are declining more slowly than road deaths, and obviously the main focus of our work is related to a vulnerable user, and obviously because vulnerable user is somehow connected to sustainable mobility. So presenter that were before highlight the importance of sustainable mobility in a urban environment, and we obviously want to offer some contribution on this. So in order to focus on safety involving a vulnerable user, obviously we need to somehow focus on vehicle speed and somehow control vehicle speed, since vehicle speed is, as you can see from this figure, is very significant in a relationship with the severity that can occur in an accident. According to the impact speed, obviously you have an increasing severity and death risk when a vulnerable user, when a pedestrian is hit by a vehicle. Usually we try to develops this sort of severity curves, just like those shown on the right part of this slide. And as you can see, there are several severity curves according to the crash scenario on which we are focusing. When you want to mitigate speed in urban areas, obviously you can have different tools, different measure. You can obviously foster sustainable mobility, try to set up cycle lane and so on. But on a more traditional approach, you can use typical traffic calming measure. And obviously among traffic calming measure, we can identify horizontal based traffic calming measures, such as for example chicanes or road narrowing, whereas we have also a vertical based traffic calming measure, such as road humps or speed table or raised pedestrian crossing. Or you can have also perceptual traffic calm measures, such as optical bars and so on. We want to obviously focusing on vertical traffic calming measure, and to be more detailed, we want to focus on raised pedestrian crossing. The interest for this specific traffic calming measure is that in Italy, according to Italian rules, this kind of traffic calming measure is can be installed practically everywhere, compared with speed humps that are that undergo to some installation restrictions. Speed humps can, according to Italian rules, can be only installed in residential area, whereas raised pedestrian crossing can be installed practically everywhere. And our research task, our research study starts from analyzing the dynamic interaction that is experiencing a vehicle that is crossing on a vertical traffic calming device, such as a raised pedestrian crossing, analyzing the vibration level that the driver is experiencing, since this vibration comfort will rules the vehicle speed when it's crossing on the traffic calming device. So we developed some theoretical model, dynamic theoretical model, in order to identify the acceleration history in terms of vibration, in terms of comfort that the driver is experiencing. And we noticed that there were some difference in obviously the vertical dynamic response according to different vehicles crossing on the traffic calming device. And we came up with the idea that perhaps this difference can be sensed also by analyzing a pedestrian crossing, a real speed profile of a vehicle crossing on a raised pedestrian crossing. So the main idea that is underlying this experimental study is that a different vehicle can have a different vertical response in terms of vibration when they are crossing a vertical traffic calming device. As a matter of fact, we are, as I told you, talking about a raised pedestrian crossing. So we need to obviously go look through some experimental data to gain the evidence of this different behavior. And so we monitor a raised pedestrian crossing that is obviously close to our faculty, engineering faculty, that is obviously recorded in this video. We are obviously in the central part of Italy, in Cassino, and this is the raised pedestrian crossing that we monitoring. And obviously we collected the speed profile of vehicle crossing this pedestrian crossing, and we obviously filter the speed profile, take into account only what we call isolated vehicles, because obviously the crossing speed can be affected by traffic flow. So we need to, identify and highlight only isolated vehicles, so vehicles that are far away from the following one in the traffic stream. Okay. So then we perform several statistical tests. The first test that we performed was a typical F-test for the analysis of variance, so when we take into account all the data collected as a whole. And as you can see from the flow chart in the left side of the slide, after carrying out an F-NOVAS test, we obviously perform a t-test in analyzing the data, obviously in pairs, in order to compare and eventually highlight the statistical difference between pairs of speed profile, speed crossing among two different vehicle type and vehicle category. Just as perhaps I did not highlight, but we consider three main categories for the vehicle: a typical sport utility car, a typical sedan, and a medium car, a medium-sized car, that are the most common vehicle category traveling on our road, I would say, in all Europe. Then, obviously, as far as the first step phase of statistical test, we verify the independence and the normal distribution of the data and the homogeneity of variance. And then following this test, we perform, as I told you, student t-test, comparing in pairs the different speed profile, and especially the crossing speed, on which we are obviously interested. And the student t-test also provide us a good response. So most of the pairs show a statistical significant difference in the crossing speeds among different pairs compare. Conclusion. The study conducted showed that how the category of vehicles influence the extent of speed of crossing the traffic calming device, confirming the initial hypothesis. To highlight a statistical significant difference in the crossing speed of the traffic calming device as the vehicle category varied, an NOVA test was first carried out which showed a statistically significant difference between the vehicle categories analyzed. Therefore, it was possible to subsequently implement an T-student test that identified the pairs of categories with the most marked difference in terms of crossing speed. Finally, obviously, a 2K correction excluded the risk of type 1 errors, consolidating the reliability of the results and strengthening the interpretation of the observed difference. These results have important practical implication on the design of traffic calming device, as currently most speed hump and also raised pedestrian crossing speed tables are designed according to uniform criteria, without considering the difference of dynamic behavior of the various categories of vehicles. Future developments obviously will include the analysis of other sides of interest to confirm or refute or reject what statistical emerged for the case study in question, but we are carrying out, we already carry out some additional data collection experimental activities on some other raised pedestrian crossing, and we obviously have a confirmation of these results. So we are pretty confident that we can try with this experimental evidence, we can develop some sort of new design methodology for vertical traffic calming device that can take into account the different dynamic response of a vehicle type. Thank you very much indeed. And I'm obviously ready to accept some question on this. Let me. Okay. Okay. Here we are. I take any question.
I have a question, if I may ask.
Yes.
Okay, let me turn on my camera. Thank you. I saw the video that you presented, and I failed to identify a vertical signal on the elevated crosswalk. Is that because it is supposed to be like that, or it is not installed yet?
No. It was not installed a vertical signal. Well, as a matter of fact, in the recent past there was a vertical signal, but it was excluded. So we can collect data without the influence of vertical signal, because obviously, as you can understand, we were interested in collecting isolated vehicles that are crossing on a traffic calming device.
I'm just asking because in my experience, the drivers seeing a vertical sign would decrease their speed, and perhaps it would affect your data, but it's just a technicality. Nothing more. Thank you.
Thank you very much for your interest question. Any other question? We still cannot hear from Turkey, sorry.
You hear now?
Yes, now, yes.
Okay.
Hi, Mauro. Thank you for your interesting work. I'm Marinella Giunta, University Mediterraneo Reggio Calabria.
Hi, Marinella.
Right. Just a question about your slide number 8. How do you measure the speed near the traffic calming device? And
from the video recordings, we identify several cross-section graphically, and we measure the time of crossing of several thresholds during the obviously preceding and following the raised pedestrian crossing. So That's how we collect data on speed profile.
Okay. I see in the slide that the speed was measured 15 meters before and 20 meters after the device.
As a matter of fact, we collect in such a way. We collect not less than 5-4 speed value, 3 precedings the raised pedestrian, and other 3 following the raised pedestrian. So we have about I would say more than 100 meters, 150 meters of road section that was covered by speed values. Because as I told you, we identify several thresholds,
Okay.
lots of thresholds. So we came up with a very huge amount of speed value for each speed profile. Okay.
Okay. Thank you very much. Bye
Thank you,
now.
Marinella.
Bye now.
Bye.
I think I'm the next presenter. So I will start sharing my screen. Hopefully it will work.
Yes, please.
Just let me know if you can see the slides.
Yes, we can see it.
Give me a second. Now, I believe now that you can see the presentation normally with no other comments. Okay, thank you. So, you can see my name. I am Efstathios Boukouras. I am a research associate at the School of Rural and Surveying Engineering. And I will present to you the key findings of our questionnaire-based survey addressed exclusively to students of the Aristotle University of Thessaloniki in Greece.
Excuse me,
Yes.
sorry to interrupt you. Can you switch to a presentation mode, because we are still looking at the presenter mode, and the slide is much more litter than the overall screen. Sorry.
The problem is that I use 2 screens, so I don't know now. I've tried.
Okay, don't worry. Sorry.
I don't know if now it's better or not. Is that the same?
Yes, it's almost the same, but don't worry. It's still readable. Okay.
I'll try my best to correct this issue. At least on my PC, I have the reading that it is on presentation mode. I'm terribly sorry about that. I will continue. Hopefully, you can see the slides. Our effort was to identify the habits of the students while crossing crosswalks on an intersection controlled by traffic lights, and to understand their perceived level of safety while crossing this cross section. And as I said, we focused on our students, on the students of the Aristotle University of Thessaloniki. I will call it AUTH just to save time. And to understand which factors influence their decision on crossing the street. And of course, at the end, to provide recommendations, suggestions, proposals for safer design of the crosswalks or the intersections, or measures to increase their perception of how to safely cross the streets. Now, in Greece, we have the most recent official data about the fatalities or on road accidents involving pedestrians are for the year 2022, as you can see on the figure, and 70% of those fatalities concern pedestrians, which is a very high value, and it's something that concerns the Greek society in general. As you can see, the risk increases with the age group. It's something we all understand the why and the reasons behind that. And we wanted to identify these risks regarding the in relation with the students of our university. We conducted a literature review using the Scopus database. We identified the number of the documents that you can see covering a time window from 2010 to 2025. And we saw that the peak publications years was the year 2020, the time period between 2020 and 2023. And the top countries with publications on this issue were China, USA, and India. Now, to give you an idea of the cross-section and the area, that the understudy area, you can see the highlighted area is the Alf campus. It's a huge area. And
sorry
yes?
to interrupt, but the slides are not scrolling. Sorry.
We see the introduction page still.
Wow. So I think that the only way to proceed is using this type of presentation. Unfortunately, going to presentation mode, it doesn't work. I'm terribly sorry. I will try again to do something about that, but I don't know if it will work. And I'm now using your time. I don't know if now you can see the slides. This is the first one, and I am at this one. You can see the presentation with the finger, the slide with the finger.
We are still seeing the slide number 2. Sorry.
Okay. Now, the only way to do it is to use this presentation mode. You can see the slide with the finger. No.
No,
it doesn't change.
Okay. I'm afraid I'm running out of options around. Let me try this. Is it better now? Did you see the
yes,
works?
yes.
Okay, I was in this slide, presenting this slide. You can see now the Alf campus, hopefully. I will try to go to presentation mode. Please inform me if you can see the slide.
Yes, we can see the slide with the campus map.
Okay. Now, this is the Alf campus, the highlighted area, and the arrow points the cross-section to which we conducted the questionnaire-based survey in situ with 2 students in the framework of their undergraduate thesis. And here you can see the layout of the cross-section with the traffic lights and the movements, the direct movements, and the movements in general of the vehicles. It is a major intersection. It is at the borders of the Alf campus. As you can understand, there are significant pedestrian flows coming to the university and leaving the university. This road is the Egnatia Street. It's a major arteria in the city. 3 lanes per direction, divided by a median with a bus lane. And this vertical road street is the 3rd of September, let's call it, street. 2 lanes per direction, divided again by a median. And you can see the traffic lights. And these are the entrances and exits to the newly operated metro line of the city. Now, the survey was conducted in January 2025. We had almost just over 300 questionnaires filled. As I said, in situ questionnaire-based survey, the students conducted the survey were at the intersection, and when a student crossed the crosswalk, they had the interview with a random sample. The questionnaire had 2 sections, the demographic section and the crossing habit section. And the first had 6 questions, the second had 14 questions. And we tried to identify, as I said, their perceived level of safety crossing the streets and the distractions and their proposed improvements. Now, regarding demographics, the majority, as expected, was under 24 years of age. And the students managed to have a rather good distribution regarding the gender. It's a balanced sample. And we had a mixed income backgrounds and car usage from our sample. Regarding how they usually cross the street using the crosswalk or not, you can see here the result, and you can see that the 60 of them do not use the crosswalk. From these 60%, you can see how in the lower figure chart how the perceived level of safety is recorded. Half of them feel moderately safe while crossing the street outside of the crosswalk. From the 244 students using the crosswalk, you can see on the right figure that half of them, almost half of them, you cross the street when the pedestrian light is green, but over 100 of them cross the street at any time, which is, of course, very disturbing and alarming. Regarding the factors influencing the participants, the students' decision to cross the walk, the first, in this question, they had the ability to answer more than one answer, to give more than one answer from these provided to them. 145 mentioned that they are influenced on crossing the crosswalk if another pedestrian starts to cross the crosswalk. 135, the indication of the traffic light, which should be higher as a value. And 104, the speed of passing vehicle. Now, let me say this. On this cross section, the pedestrians, while crossing the crosswalk, the vehicles turning left have the ability to cross at the same time, because when they approach the intersection, the traffic light that they can see is a flashing yellow arrow, which according to the Greek driving code allows them to move, to turn left, but at the same time they are obligated to do it on cautious and provide the right of way to the pedestrians. This means that the pedestrians cross the crosswalk, but at the same time they have vehicles turning left, so there is the possibility of meeting the vehicles, the pedestrians, and the pedestrians, the vehicles. However, the Greek driving code it makes it very clear that the drivers must stop and provide the right of way to the pedestrians. Regarding what makes the students, the participants, feel most insecure when crossing the crosswalk, you can see that again they had the ability to answer in more than one answer based on the provided ones. 104 of them say that the drivers running the yellow light, which is normal to feel insecure when you see a vehicle coming, and then the simultaneous passage of vehicles and pedestrians, again, it's quite relative. And on the next question, regarding the perceived level of safety when crossing the street and at the same time listening to music using headphones, the majority of them felt quite safe. When talking with friends, the majority again felt safe. Using their phone another way, texting, video watching, not talking or listening to music, the majority felt slightly safe. And when talking on the phone, the majority felt moderately safe. About the frequency of crossing the street and at the same time using their mobile phone or another mobile device, the majority of them, when crossing the street and listening to music using headphones, mentioned that they do it often. Talking with friends, again, often. Other phone usage, rarely, and talking on phone sometimes. Now, we asked the students to provide any improvement, to propose an improvement on how to improve the safety level of the intersection of the crosswalk. And the first one had to do with the installation of countdown timers for the pedestrians. Cameras to monitor the pedestrians' movement and the vehicles' movement, and horizontal signs and markings for the pedestrians. And of course, the necessity of installing better vertical signals for both the pedestrians, the students, I mean, and the vehicles. And of course, waiting areas where the students, the pedestrians can wait between traffic lights. Concluding, what we find out was that there is a group dynamics affect behavior. I mean, We saw that they are affected, the students, when someone else tries to start crossing the street. That the awareness doesn't always ensure compliance. They know that they don't feel safe, but nevertheless, they cross the street. The distraction and urgency are key influencers for their decision to cross the street, and they value safer infrastructure and enforcement based on the proposed measures. Countdown signals are highly appreciated by the students of the Aristotle University of Thessaloniki, and time-sensitive behavior requires more attention from all decision makers. We know the limitations of our approach. It is limited, of course, to the students of the off-campus and at one intersection, and we know that we want to expand our research to other demographics, other intersections, and to other cities as well. And of course, test the effectiveness of the proposed interventions. That was my presentation. Thank you very much for your attention, and I'm at your disposal for any questions. And sorry for the problems.
There are no questions from Turkey.
Okay, thank you.
Thank you so much for your presentation. Any online participants? No. Okay, thank you.
Professor, you can start.
Okay, thanks. Good morning. I try to stay in the 10 minutes that the organization give for each presentation. And I would like just to discuss about the problem of risk reduction in urban areas by means of evacuation. In the specific, we can speak about the problem of designing a specific survey to evidentiate the result that you can obtain if you use emerging information communication technology. The problem of research depends on the very great number of displaced people due to conflict and disaster that we have around the world. In the last 10 years, about 2.5 million of people was displaced. But regard this very great problem of all the world, of all the people, of all the state, we see that there is a very little attention from the different states. Yes?
We don't see the presentation of the slide. We see only the first slide.
But you have... sorry, I don't know.
Wait, are you in the first slide or are you talking about the graphics?
In the second. Now it's in the third.
Okay, it didn't change.
Okay.
Professore, deve condividere la presentazione, non il PowerPoint.
No, io must share the desktop, not the presentation.
with the smartphone. Questo moment.
Spiegaglielo passo passo come fare.
Sì, Marisa, il problema è che sono con lo smartphone, capito? Perché c'è stato a rete, se n'è andata, capito? E quindi non vorrei che lo smartphone non mi sta facendo aprire la cosa.
E se no, può andare avanti senza aprire la presentazione, senza modalità presentazione.
Però devo dire perché non ha visto.
Marisa, allora mettici le slide tu e ci spieghiamo prima.
Va bene.
Però scusami, adesso non si vede?
Sì, adesso sì, però deve andare avanti.
Adesso si vede la seconda?
Va bene, perfetto.
Yes. Now.
La seconda si vede?
Sì.
La terza?
Sì, perfetto.
Vabbè, proviamo in questo modo. Ok. Then, as you can see in the right part of the slide, there is this very big number of people that each year is displaced around the world. We arrive at 200.5 people that was displaced in the last 10 years. But we have a very great attention by means of United Nations, but you don't have the same attention by the different state, the different people. And then we need to have a common global organized evacuation strategy as indicated by Sendai framework. In this general framework, we want to study the gap that there is between theoretical planning and practical implementation. And in the specific, we want to go in deep in the recovery increasing by social knowledge. In this case, we have different objectives. The first one is to analyze the dynamic behavior of transport user under risky condition, but we want to arrive at to define a simulated emergency procedure and improve evacuation planning. This is our general scope of our research. Then we want to present three different parts. The first one is the state of the art. The second one is a design of an RPSP questionnaire to the user. And the third is to give you the first statistical results about the behavior choice for the path. The emerging information and communication technology is a great problem that we have in different parts of transport, of study on transport. And the main technology that we consider is Internet of Things. In general, with the Internet of Things, IoT, you can study what happened in the other part of the network when you stay in the network. With big data, you in general can consider what happened in the past time, in the past period, in all the part of the network, also in the part that you don't know because you move in different part. But with big data, you can know what happened in the different part, in all the part in the network. The third level of ICT is the blockchain. The blockchain is very similar to IoT, but consider the value that you exchange in the network. And for this way, for this motive, generally, you can define blockchain as Internet of Value. The fourth one is the artificial intelligence. And you know that artificial intelligence can use it in different contexts and in different contexts of mobility. And the five that we can consider in the emerging ICT is the digital twin that give you the possibility to simulate in a very advanced form your network, your problem, the risk on the network, the different aspects that happen in the network. In this case, we want just to define the general framework of the methodology in the two main steps, the state of the art and what happened for the path choice model in the exposure. If we present just a very short state of the art, we can give indication about three levels that we need to consider. The first level is the level of the literature about transport risk analysis. There is a very great long literature on transport risk analysis that derive from the very important study conducted in USA, mainly after the Twin Tower attack and the Katrina storm, because after these two very big disasters, the USA organized a very in-depth research, but we don't have a similar in-depth research in European country. European Union is more focalized to organize what need after the disaster, but in Europe they study the research to reduce the what happen during the disaster is very few and the research is very small. The very interesting research is just in USA. The other country in Europe, in Asia, or in the other important economy don't study this aspect. The second great element is the transportation system model. And as we can see just in 1 minute, the transportation system model is the core model that you can use inside the transport risk analysis to study what happened to evacuate in a city, what need that you use to study the evacuation in a city. The third level is the use of emerging ICT inside the transportation system model. And then, in general, you know what happened in transportation system model in ordinary condition. And in ordinary condition, you can study what happened in the daily flow. If you want the emerging ICT inside the transportation system model, you can use stated preference. But if you want to study what happened in extraordinary condition, it need you use stated preferences for transportation system model and stated preferences for risk flow. For TSSM with HT. In this case, we can state that ordinary condition is the very ordinary research, the very ordinary sample, the very ordinary interview that you can make. In extraordinary condition, is important that you use stated preference, because just stated preference can present to the user the extraordinary condition. In this case, the formulation and then the second part of the methodology is just in the formulation. Transport risk analysis have this very diffuse formulation for which the risk equation derive from three elements. The first element is the occurrence relative to the type of event in the propagation in terms of effect. The second element is the vulnerability. The third element is the exposure. In general, you know that the occurrence is studied by different body of the state, for example, the secret services for terrorist attack as the Twin Tower, or different meteorological agency for the problem of storm, of rain, great rain, and so on. The vulnerability is specific studied by researcher on infrastructure, on structure, on different mechanical or geotechnical element. The third part of risk, that is exposure, is very low studied, because the exposure, as I told before, for example, in Europe or in Italy, is just studied in terms of what to make after the disaster, then after the deed, after the displaced, and so on. We underline that the exposure is very important during the disaster, or in the time between the event and the effect on the people, the event and the effect on the person. We know that during this time you can reduce strongly the debt about the disaster. Then our study is just in this element. We want to study the exposure to reduce not after, but during the occurrence, during this element. Then we can consider the TSM, as I told before, inside transportation risk analysis. Then, if you introduce the TSM, you can formalize the flow, and then you can formalize the H vector, that is the vector of the flow inside the network, and G vector, that is the vector of utility or cost during the network. Then, in this case, we can formalize different level of dynamic models where we can consider introducing, as I told, as I want to underline again, the role of ICT. Then you can have 3 different levels of study. A first level is if you consider in a very general dynamic model a leg 0, that is the entry level to study this element. The second is leg 1, that in general give you classical, very known different temporal series, or leg 2, that is a very advanced dynamic model, but is very difficult to calibrate and to validate. In this case, we can simulate path choice of user over time. But the problem is to introduce the ICT inside the path choice. Then we want to know as the user perceive the ICT during a specific event and in the time that happen during from the event to the effect. Then in this case, we can we need to structure a specific stated preferences questionnaire. We just to refer, we consider the city of Reggio Calabria. We want just to remember for all the participants that the earthquake in Reggio Calabria was the first, the main disaster around the world for an earthquake. What and in Reggio Calabria and Messina, around the Strait area, we have just 100 of years ago about 100,000, more than 100,000 of death during the earthquake. Then is an area very important to study what is possible to make to reduce the death. In this case, we can consider fixed the emergency occurrence. In this case, we consider a violent storm with flooding risk. We consider the condition of vulnerability fixed. And then this is the element exogenous to our questionnaire. We told to the user, to the reviewer, this is the situation. You have a violent storm and you have a specific condition for infrastructure. The element that we ask explicitly to the people is a first level, basic risk. Then you say during the, for example, you say in the network, what do you make as you choose the path to use to arrive in the safe point? The second element is the second type of question that you give to the people interview is, you have a risk, but you know what happened in different path in the network, and then you can choose not only with your information, your historical information, but the information that arrive from all the network in this moment. The third element, and then the third part of the research, is to give information from the other link in the network from the other part of the network, information about what happened in the next period, and then in the link that you can make, that you can choose. This 3 level of information is tested in a very schematic network where you have a 2 main rod. A first rod is an highway, the green presented in the right part of the slide, and an urban rod. But these 2 different main rods as intersect in 2 main macro node, the first macro node, the second macro node. In this context, we give different elements to the user, as I told before, with a first questionnaire where we present the results, where we present what happened about the occurrence, the vulnerability, and the second element is relative to the different but choice. We ask about the different choice. After the first questionnaire, where we present what is the problem, the event, the effect, the occurrence, the vulnerability in the external condition, we introduce a second questionnaire. In this case, we introduce the different emerging ICT. In the specific, as I told before, the emerging ICT relative to big data, and with big data, you give the information about all the paths in the network, all the paths at your disposal. And with the other level, we introduce the IoT and then the information about what happened in this moment, and then in the link that you must choose, in the link that you go ahead in your choose. In this element, we can obtain the result. We have the first prototypal sample with a very different condition for gender, for age, for level of education, for main transport mode at the disposal for the user. With this general sample, we introduce the questionnaire respect the questionnaire 1 and the questionnaire 2. The questionnaire 1 is relative to and this is the very first result. You have you have my last slide where you can read the comparison of the third information level. Sorry.
Yes.
Yes, you have. Perfect. This is the third one. In this case, you can see that there is different result. The first result is for the stated preference level 1, where you don't have information about emerging ICT. With the second SP stated preference level, we have information just about big data. With the second questionnaire, you have information about the introduction of IoT. And with IoT, you have different elements with different conditions that you can consider. Okay, in this case, we can arrive at the last, slide where we have feature development. Is evident that our research is important because it belongs to the discussion-based exercise that as United States teach all us. You have a different level of discussion-based. We stay inside the table type exercise. We want to integrate this result and we want to calibrate the model that derive from the different result, and the first model that we study is the model at lag 0 with the introduction of HCT. The second group is the one presented in this slide. We move from lag 0 model to lag 1 model. Then when you have memory of what happened in your network and in your choice. And the third element is when you move from the classical lag 1 for each node to a very advanced model where you study what happened in the H vector. I underlined that some slide ago, we presented the H vector as the vector of flow on the network, and then you can know what is the H vector in the time period W respect to the H vector in the time period W minus 1. In this case, it's important to calibrate the matrix R, because the matrix R give you the possibility to move from one period to the next one. I want to just underline that around the world, the calibration of matrix R is very few, and then you don't have a very large literature. You don't have literature for matrix R, and then this is the first, I think, experiment to calibrate the different model, because as you can see in this very, very small example, you have a specific model for each path from where the user arrive. Then we hope that with this result we can give an advancement for all the research about the risk, with the very important, I think, objective, the very important goal, that is the goal defined by United Nations, that is to save a very great number of human lives in different contexts: terrorist attack, natural disaster that produce, as I told in the first slide, in the last 10 years, I want to conclude with this consideration, 200.5 million of displaced people. Thanks.
Thank you so much, Professor. Are there any... Yes, we have one question. Can you hear us? Okay.
Professor Marinelle speaking. Congratulations.
Good morning. Good morning, ma'am.
For this work. It's very interesting in the era of climate change and in the era in which extreme events are frequent, unfortunately. I would ask the hypothesis on the state of the infrastructure in the assignment model. You consider a loss of capacity of the road, or how do you take in account the state of the infrastructure, transportation infrastructure, particular roads? I think.
Thanks for your question. It's important, this question, because this question, as you can think, and we can discuss directly in Italy, the hypothesis about infrastructures here is very important, is crucial, but we wanted to stay in our part of research. If you consider the general model, you have, occurrence times vulnerability times evacuation. Then your hypothesis is inside the vulnerability. Then the definition of vulnerability for very specific risk derived from our study. But as you can think, as you can very derived from other research field, as for example, research on road infrastructure, building infrastructure, and so on. Then the model of evacuation start when finish the vulnerability. Then with the different scenario of vulnerability, we can introduce the evacuation. In our case, for example, when we propose the questionnaire, we introduce 3 or 4 different vulnerability situation, but is not important, is not our field of research. We can just to give to the person, you can have the bridge disrupted, so on. Okay, is evident. And then we can study different network under different vulnerability condition.
Okay. No, I know. In italiano, no, questo lo comprendo bene. Volevo capire se poi il parametro che voi prendete, questo non attiene ai vostri studi, quello di valutare la vulnerabilità, ovviamente. Volevo capire quale parametro poi voi vi perdete. È una ridotta capacità? Nel caso in cui, cioè il parametro capacità, perché nell'ipotesi in cui diciamo la strada comunque continua a essere in esercizio, oppure cancellate quel ramo dalla rete. Ecco,
vari livelli. Ci sono vari livelli.
Ok, vabbè, avremo modo di chiacchierare su questo.
Certamente.
Ciao professore, arrivederci.
Arrivederci, professore.
Grazie.
No. Any online participants would like to ask something? No. Thank you so much, Professor.
We now have a general session with the risk, if I don't remember that. Now there is the general session with the risk, with the disaster preparedness, a risk, if I don't remember bad.
There's a keynote speaker, yes.
Sorry?
Yes, there's a general meeting, a keynote speaker.
Yes, but it's just on disaster preparedness, a risk.
Yes, let me check the calendar. There is a professor, there is a coffee break for 20 minutes, and then at 11, the speaker will start.
Okay.
Okay, thank you so much.
Bye.